We say that an agent is learning if it improves its performance on future tasks after making observations about the world. So if we have an agent that can do something in the environment, let's say it does task S, and we show this agent something about the environment and let it make observations from the environment, right? And then we ask the agent to repeat the same task, task X again. If upon observing this environment, the agent improves its performance for the same task X, then we say that the agent is learning. Now, this learning can range from something very trivial to something very profound. An example of trivial learning is jotting down a phone number, which all of us can very easily do, right? An example of profound learning is inferring a new theory of universe, and only a few of us, like Einstein, can do this. So there's a huge range in which the learning can be defined. In this chapter, we will focus just on one class of learning problems. And this is a specific or a special type of learning, a subset of learning, where we will try to learn a function from a collection of input-output pairs to predict the output for new inputs. In other words, say for example, you have certain inputs and you have the corresponding outputs of these inputs, right? And we also have, let's say, similar new inputs, but we don't know their outputs, right? What we would like to do is build a function f that learns from these input and output pairs so that when we feed the new input to this model, it can make predictions of these outputs. So this class of problem is what we will focus in this chapter. And you may think that this is a very restricted class. I mean, it's a very small subset of what learning exactly means. But surprisingly, such a learning has a vast applicability. Any component of an agent can be improved by learning from the data. These improvements and the improvement techniques that we use depend on four major factors. That is, which component is to be improved? Are we trying to improve the vision of an agent, or are we trying to improve, let's say, the way the agent picks up objects? For instance, workout improves muscles and not mind power, right? What prior knowledge does the agent already have? If we bring an agent that is already good at path planning, then we don't need to train the agent on that. We may need to train the agent on other things. What representation is used for the data and the component? For example, logical agents may have a different technique of representing the data. Some of the data that the agent uses may be in a tabular format. Some may be in a totally different format. Does the agent use the model of a human brain, neural networks, to do the learning? So the representation of the data and the component also matters. What also matters is the feedback available to learn from. In other words, is it reinforcement learning? Is it that we want the agent to learn something at once at the beginning and then later implement it? Or do we want the agent to learn a little bit of things at the beginning and then iteratively learn as it interacts with the environment? We will look into each of these separately. Let's just start with the components to be learned. So what component to be learned is also very important for an agent. These days, many agents are something known as end-to-end. In other words, you feed your input to the agent and the agent directly produces output. You don't do any kind of data processing in between. You directly submit the input to the agent. So those are end-to-end systems. But most systems are not like that. Most systems have various components in them. Let's look at an example of a taxi driver agent. A taxi driver agent may have many components. One important component may be a component that listens to the instructor for something like brake or some important signals like that when he or she shouts. That should be a separate component because it has to function even if everything else fails. There may be another component that detects pedestrians. There may be another component that detects weather conditions and detect other vehicles. And then there may be a next component that takes input from other components' output and then makes decisions. So it's important when trying to learn an agent to understand what are the components involved, and what am I going to learn, if I'm going to learn these components separately or together, and so on. Here are some examples of representation for agent components. One example is the input data formatted for propositional and first order logic. If your agent is a logical agent that deals with true, false, and true false statements mostly, then it would be ideal to use propositional logic or first order logic as a technique of representing your data and your model. If your agent is something that is like a decision theory agent, then Bayesian networks are ideal for such situations. However, most of the current machine learning research covers inputs in a form that is a factored representation, basically a vector of attribute values. And the outputs can either be a continuous or a numerical value. Here's an example of such a factored representation dataset. The iris flower dataset was curated long back, but it is even now very frequently used to understand how machine learning works, how AI works, and so on. This is a very small dataset, and this is how the dataset looks like. This is a very small dataset. It contains 50 samples from each of the 3 species of the iris flower plant. The 3 species are Setosa, Virginica, and versicolor. And there were 4 features measured from each of the sample, each of the plant. The length and width of the sepals and petals in centimeters. So let's look at the first record. So what this first record means is, for this plant number 1, the sepal length, basically the length of this green part of the plant, was 5.1 centimeters. And the sepal width was 3.5 centimeters. Petal length was 1.4 centimeters. Petal is the inner part of this plant, and petal width was 0.2 centimeters. And this plant also belongs to this class of Setosa. Similarly, we have other plants. Plant number 2, these are the details. And as you can see, this is like a vector of your input features or inputs. Vector with 1, 2, 3, and 4 items in the vector. And here you have your output label. In this case, this is a 3-class classification problem. In other words, given this data, what you want to learn is to build an agent A that can take these 4 numbers as input and predict what class the plant belongs to. So say, for example, if we took out of this 150, if I took only, let's say, 100 examples and trained an agent to learn correctly classifying whether each of these 100 examples belong to Setosa, Virginica, or versicolor, then after the training is complete, this agent, given a new data, given a new vector of these values, should be able to predict whether that plant belongs to which class this plant belongs to. The next important thing to look at when we consider learning is to look at what feedback it is available to learn from. And there are 3 types of feedback available that determine the 3 types of learning. The first type of learning is unsupervised learning. And in this learning, the agent learns patterns in the input even though no explicit feedback is supplied. In other words, you have your data, but the agent does not have the correct output label to learn from. So the agent has to learn by looking at the data itself. Here's a very common example. One common example is something known as clustering, that is grouping data by looking at the input features. Something like this. Where do you want to look at the input features? Maybe if we are looking at the previous example, maybe this is a cluster where the petal length is very small, right? And this may be a cluster with petal length as medium, and this may be a cluster with petal length as very high values, right? So in this way, even without looking at what class these plants belong to, we can cluster them, group them. And this is an example of unsupervised learning. Another example is, let's say a taxi driver agent wants to learn which days are good traffic days and which days are bad traffic days. So what we might do is, so we have this taxi driver agent, and the agent may know, like, we may tell the agent, looking at the weather or like weather app, whether the weather is good or bad, whether good, whether bad. But then over a period of time, the taxi driver, without using these true labels or predictions, may know, looking at the morning and many other things, be able to predict whether some day is a good traffic day or not, right? So such type of learning, where you don't look at the output but basically look at the inputs to do the learning, is unsupervised learning. The next type of learning is reinforcement learning. In reinforcement learning, the agent learns from a series of reinforcement, or also known as rewards or punishments. So what happens is, let's say we have an agent, it takes an action and interacts with the environment. There is a processor that you have that interprets the environment, and then if the agent made a good action, or an agent that is rewardful, then the agent will receive a reward, and the agent will continue to work towards that action or improve that action. If, however, the agent doesn't receive action, or gets a punishment, or gets a low score for its action, then the agent learns to minimize that action and maximize some other kinds of actions. One simple example would be, if a taxi driver agent at the end of the journey receives a very little tip, then it is an indication that the taxi driver did something wrong, right? So then the taxi driver agent can learn to do something better next time. The next type of learning is supervised learning, and this is the most common type of learning that we will do in AI machine learning. In this kind of learning, the agent observes some examples of input-output pairs and learns a function that maps the input to the example. And a very good example is the iris dataset, where you already have a table that has your input vector and then your output labels, and then what you have to learn is a function that takes this input and predicts the output. In practice, however, the distinction between these three types of learning, that is supervised, unsupervised, and reinforcement learning, is not always so crisp. There is a lot of overlap between these three learning techniques. And also in between lies something known as semi-supervised learning. In semi-supervised learning, only a few labeled examples are given, and we need to make what we can of a large collection of unlabeled examples. In other words, your data may be part one, where you have labels, and your data may have another larger chunk of portion, part two, where there are no labels for this stuff. So what you want to do is build a learning agent that can look at these labeled data as well, and also look at these unlabeled data and then make predictions or learn a model. Here's an example. Imagine that you're trying to build a system to guess a person's age from a photo. So given a picture, what we would like to do is build an agent that can take this picture as input and then predict the age of this picture. In supervised learning, what you do is you gather some label examples by taking pictures of people and asking their age. So you have a first set of all the pictures in your as your inputs. So these are your inputs, and then you have ages as your output labels. You try to learn a function that maps these pictures to the ages, so that when you feed a new image to this function, it can predict the age for that person. So supervised learning is pretty easy. In reality, what happens is some people can lie about their age. So some of these ages that you have are incorrect, right? Now, it's not that this is a random noise in the data. There's some pattern. In other words, there are inaccuracies which are systematic. And to uncover them, we can use unsupervised learning. What we can do is cluster these pictures into various clusters and see if there are people who and try to identify people who may have inaccurately reported the ages, and those we can throw them out of our data set or do something about them and then continue our supervised learning. So this is how we may see the overall problem as first unsupervised learning and then later supervised learning, and it becomes semi-supervised learning overall.